identified some kind of condition that affects some students that I just call difficulty with focus. So, like, you know, if you did this, you shouldn't feel bad, because apparently other students did it too. There was I'm just making something up here. There was a problem on the exam, something like, maybe it was, and looking at that, some students didn't immediately identify this as a product. Right? And it got me thinking about how, well, how do you make that mistake? Well, you use these symbols here for two totally different things. I mean, some people are confusing this as, you know, like cosine of x, somehow. That this is just, you know, trying to isolate this and do this first. This is saying what's in here is the target of the function. And I'm not, you know, knocking, you know, like, nobody's stupid here. It's just like, how do you make that mistake at this point in your math career? It's some kind of difficulty focusing. There was another thing I saw in a couple of places where I wrote down like this. It's an interval. But a few students kind of thought, well, it was like the point, -2, 4. And if I write this as an open interval, it's indistinguishable except in context. So yeah, you know, now in defense of the curriculum and so forth, a number of you are computer science people, and when you start programming, well, you'll have a compiler or something that will tell you when your syntax is wrong. But you can write perfectly valid things, misunderstand the syntax, they'll compile, run, and you'll find you don't get the right answer. Because attention to detail in computer science, you know, when you're writing a program, well, like I say, the compiler will often tell you if something's really wrong, but often bugs are just because, you know, it's attention to detail. You have to focus. Again, I realize this is not computer science class, this is math class, but I'm going to give an example from computer programming. So, in almost every language you're going to come across, you could have a statement like this, x equals y, and then you could write, you know, that would be like a computer statement. If this is true, then do this. If this, do this, this is a statement. But it's equally valid to write this. And you might think that these are curly braces that mean everything, treat everything in here as if it's just one statement after this. And both are correct. I mean, the computer will do the right thing. After, I don't want to say, 40, 50 years of programming, we could program BASIC in high school. It was really unusual back then. They had to hook us up like teletype to a computer somewhere. Nowadays, any kid can get a computer and do this. But But I learned to always put these here and to always indent them the right way. Even for something like this where it's totally unnecessary. And there were two reasons. One is just visually, if someone's looking through, it's like very clear. Every if, has a body like this. The other reason is you get statements like this. X equals Y. I'm just making stuff up. It doesn't mean anything. Now you look at that and you go, okay, if X is 4, we're going to do this. And this is a, if statement. But wait, there's two ifs here. What if I wrote it like this? Well, now I know a number of you must be learning Python, where indentation actually means something. So that's one possibility, that this else goes with here. But if you're writing in C or any plethora of other stream languages, it doesn't matter that you did this. It still goes here. And okay, if you follow my rules and put your curly brackets in everywhere, then it's unambiguous, and your indentation is unambiguous. And this may not be a good example for what we're doing in class, but again, the idea is you write something, you have to be very clear about what it is on the paper and in your head. You have to be a little patient with these things. Anyway, so that's my blather for the day. I guess I didn't release the homework till this morning, and it's not due till next week, so I probably don't have any questions on the last assignment yet. But if there are any homework questions, you're welcome to bring them up. What about other things? Okay, so we're going to talk again. We started talking about definite intervals. We have some notation. We have a symbol here. We give it a starting point and an end point, some function, and then just we add notation, which it just tells you what the variable is here. X. It's a dummy variable. You could make it Y or T or anything. It doesn't matter. And this represents, first of all, it represents a number. Right? But it also represents, this is our function. This is A, this is B. It represents this area. And even though I use the term area, which implicitly is a positive value. We saw on Tuesday that you could have a function like the sine, and if you integrate from point A to point B here, you're going to get 0 because below the line this gets added up as negative area. And we saw a couple examples. We saw that if the function is a constant function, well, you get a rectangle, and the area could be expressed as, there's a constant cx, as bx minus a. Let's see in here, bcx. If the function is a constant, it just so happens that this value here, this antiderivative, it's an antiderivative. It gives us the right value of the area. And we also saw that in the case of simple function f of x equals x, where we can write this as, and using this, we're using a different notation for the square brackets, but again, we run into what is the antiderivative of the function. So the question at hand is, if I take some integral, and I find the antiderivative of f of x. I have some antiderivative whose derivative is f of x. Not just the examples I gave, but in general, can I say that that's f of x for a b, or for b minus f of a? Now, that in a way feels pretty astounding, the idea that you just have some function, very complex function, and you pick any 2 points on it, A and B, and you find the area by merely evaluating the function at one end and the other. That's what we're going to find out is the case. Yes?
So basically, to find an area, you would take the antiderivative of both points and then subtract.
No, you take the antiderivative of the function.
Of the function, but would you use the point? Like that point A, plug in, like say if it was a function, would you plug in B? So like f of B would be the function of B plugged in? That's what I'm asking. Like say if you have x squared.
I'm getting communication gap here mostly because of volume.
I was asking
This is just notation meaning this, right? And I'm saying I have an integral I want to evaluate. If I can find the antiderivative of the function, which is this capital F, I can find the value of this integral, the area, by merely evaluating this.
You answered my question. I would that.
I did?
Yeah.
You're sure? Okay. All right. Well, this is a beautiful result of calculus. We're going to look at it in a more abstract way a little later. But as a first step, I think we want to get some view that this is actually the case. Maybe there's some way we can figure this out. We can see this. So that's what we're going to do next. We're going to go over why this might be the case, and it involves a little bit of algebra, some math, some limits. And if you want to really kind of be in touch with it, you're going to have to focus. So let's try and go over this. Okay. So we're going to start by defining a function. We're going to call it f of x. We'll put aside the meanings we've had before. We'll come back to the idea that this has an antiderivative. And we're going to define it in a way that we haven't quite, we haven't done anything like this yet. So what are we doing here? We have some integral from a to some unknown point, x. And we're integrating from a to x. Again, I'm using t here, it's just a dummy variable. And I'm stating that this represents the area from a to x under this function. So let's take a look at what it would look like. I have some function here, f of x, and we're going to put a at the origin here to make things simple. We have some point x. And what does this integral represent? It represents this area in here. So now I want to add a little something here. I want to change this to f of x plus some small constant h that we're going to look at. So this just becomes the same integral. And we want to see what this looks like. Well, h is just some little value here. And what does this integral represent? Well, it's all the area in the first part plus a little more. So this is the area from a to x, and this area is the area from a to x plus h. And now, in a very manipulative manner, we're going to look at what is f of x plus h minus f of x. Well, if f of x plus h is this area, and f of x plus h is this area, and f of x is this area, their difference is just the area in here. Child and color code green. Now, if h is small, this is kind of like a rectangle. Right? If h is small, you can approximate this as a rectangle. And that rectangle would have what? It would have the area of, approximately f of x, or f of x plus h, times h. So if we divide it by h, it's approximately the value of the function. Say this correctly. So we're now going to look at the limit as h approaches 0. F of x plus h minus f of x over h. Which, again, this is approximately f of x. Well, we want to look at the diagram now and think about that. As I said, this is approximately f of x, but it's really, again, approximately f of x. This is a function plus h plus f of x over 2. Now, I want to make that really clear here. This is the area in the green area. If I divide it by h, as this gets very small and is a rectangle, it's approximately the function at one of these 2 points, f of x or f of x plus h or something in between. So if we add those 2 values and divide by 2, that's what this is approximating.
Is that just like the average of the values?
Yeah. If this was a constant function, then it would absolutely be the average. So this is just, again, it's an approximation. But we can evaluate this. I mean, we start with the assumption that f of x is a continuous function. If it's continuous, its limit is the value at that location. So what is this? This is f of x plus f of x over 2. I hope I got the constant right there. No. Yeah. This is just f of x. Now I have to think a little here. What have we done? We found that, I guess I'll rewrite this, that if f of x is equal to this integral, we take the limit of this function, f of of x plus h minus f of x over h. But what is this? What is this the definition of? That's the definition of the derivative. So what we conclude is the derivative of f of x is equal to big F is f, little f of x. That was a lot. You may want to ask questions, you may want to try and take that in. Just looking at this diagram, looking at the area as we squeeze this down. And what do we find? We find that this function here, which is this integral, its derivative is just f of x. Okay, so what's the takeaway? It was what we were looking for. If you have some function f of x and you want to find an integral, I guess I should write this way. If we can find a function whose derivative is f of x, that is an antiderivative of f of x, then we can evaluate this in this manner, which is just what we were doing with the constant function and f of x equals x function. But now we see this is just, in general, it's true. There's some restrictions here. We need a continuous function. That actually can be loosened up. What else? We haven't really addressed the issue of negative area. We're not going to do that formally. We're just going to look at the consequence of that. So this is it. This is like big news. We don't have to learn some entirely new branch of mathematics to find areas. We know how to find derivatives, and consequently, in cases where it works, we can go backwards, find an antiderivative. Now we can find the area under curves. We can evaluate definite integrals. Well, this isn't a definite interval. This is a definite interval. Just because it's probably confusing, I think I want to point this out again. If I have two values here, a and b, and I evaluate this integral, it's a number. This construction here, it's kind of saying like a function whose output is an area. If you give me an x, it becomes a definite integral. But this is a function of x. That's why this whole thing works. All right, this is the big takeaway for today. We're going to do some examples on how to apply this. But are there any questions at this point? All right. Standing, right? This has been waiting for you for a few weeks. All right. All right, with that in mind, let's do some examples, get some of the mechanics of this down. All right, we're going to take a problem. We've already looked at this to some degree. We have a curve y equals x squared. It's a parabola, of course. And we want to know its area on the interval 2, 4. So we got a point here, 2, we got a point 4. kind of this area that we want to calculate. So let's write this as an integral. It's the integral from 2 to 4 of x squared dx. To solve this, we need some function f of x whose derivative is x squared. Well, we were looking at that last week. We were looking at antiderivatives using the reverse power rule, which would be that if f of x is x to the n, f of x is x to the n, then the antiderivative is what? We know it's going to be n plus 1, so that the constant comes out right, we divide by n plus 1. So here our f of x, here our antiderivative is just what? It's just x cubed over 3. So this becomes x cubed over 3 evaluated at 2 and 4, which is 4 cubed over 3 minus 2 cubed over 3. It's that 64 minus 8 over 3. And we find our area. It's pretty simple. Seems pretty simple. We're not limited to polynomials. Take function f of x is cosine of x, which kind of looks like this. And we could ask, what's the area between pi over 3 and pi over 2? So that's the integral from pi over 3 to pi over 2 cosine of x. You know, before I go forward, I want to make an observation. Usually when we talk about antiderivatives, we talk about it having some added constant. You may have noticed when we're evaluating a definite integral, well, we could add the constant and subtract the constant. So it doesn't really, you don't really need to keep track of it. All right, so what is the antiderivative of cosine of x? Anyone? We've got to think backwards. We're not doing derivatives, we're undoing derivatives.
Negative sine x plus c.
I'm glad you stepped in that mud puddle. The derivative of the cosine of x is the negative sign.
Would it be cos x squared divided by 2?
I know how you got there. I think it's worth kind of looking down that wrong alley for a second. So what you're kind of saying is cosine of x.
Sine of x.
Oh, sine of x?
No, that would be the antiderivative.
Wait, we're going to get there. We'll get back there. Patience. No, Jimmy brings up a good point. This is a function to the first power. Maybe the antiderivative is the cosine to the second power over 2. Let's work this forward, because that's the way you can always test your antiderivative. Let's find the derivative of this. This is 2 cosine of x over 2 to the first power. Oh, but the chain rule tells me I have to multiply it by the derivative of the cosine, which is the negative sign. Well, we don't have that here. Right? If we did, if this were cosine negative sign, then you would be right on target. All right? We're going to look at how to do those more complicated antiderivatives in context, but it's good to, this is just very simple. This is just sine of x. Is that what you said, Michael?
I just looked at the derivative.
Okay, all right. All right. Again, our check is what's the derivative of the sine? It's the cosine. Always good, to check these, especially in a case like this where it's kind of confusing. Normally, we're used to thinking derivative of the cosine, it's negative sign, but we're going backwards. Right, so now all we have to do is kind of sum up our trigonometry skills. This becomes sine of pi over 2 minus sine of pi over 3. Now, I know there's going to be a bit of a knee-jerk reaction to grab your calculator, but at least this isn't some carpentry problem where you're going to use a ruler. You just need a decimal number. Let's think about this. Sine of pi over 2. Right, that's pi over 2. That's 90 degrees. What's this? Anyone? Sine of pi over 2. Yes, George. It's 1. And then we also have sine of pi over 3, which is 60 degrees, 60-degree angle. So here the hypotenuse is 1, the cosine down here is a half, and this becomes square root of 3 over 2. All right? I warned people at the beginning of this class, you're going to need all that stuff. Struggling to remember here, some of you. Not everyone. Okay, so what is that? Well, it's just the area under the curve between pi over 3 and pi over 2. Actually, no, that's not. That diagram is wrong. It'd be more like this. Still a bad diagram. Just to give you the idea. Okay. All right. Let's do something that calculation-wise is really easy. Take the function to the x, right? Exponential function. And let's find the area under this curve on the interval 0 to 2. So we write that 0 to 2, e to the x, dx equals, and then some antiderivative. This should be antiderivative of e to the x.
Yes.
Yes, oh, lovely. So this just becomes e squared minus e to the 0, which of course is just e squared minus 1. I mean, you know, the calculation's really easy, but all of a sudden, we go from limited to rectangles and circles and things. Now we can find areas under any curve that we can find the antiderivative of. All right. Now let's go back to that question. That has to do with some function where the function is below the line. F of x is less than 0. And we want the area underneath here. From some point A to some point B. And we're wondering what this integral will be. So here we have to go back to the definition we looked at before, where we treated this area as the limit as the number of rectangles gets infinitely large and the distance between these points gets small. Again, this is just saying we're estimating this as rectangles where we take the height as f of x on some point here, and delta x as being the width. Well, what happens? What happens to this sum? This being this integral from whatever. I guess from our A to B. Well, you can see right away that all the values of f of x are negative. They're all below the line. So our integral here itself is going to be less than 0. We're effectively creating an idea of negative area. If you're actually dealing with real geometric areas, it doesn't make sense, but in many problems, we have some function and, I guess a good example would be if we're traveling at some velocity, and then we reverse. We start going in a negative direction. Well, we're going to traverse a certain amount of distance, that's our area here, and then when we turn around, we can just kind of start subtracting it until we get back to where we started from. So, all right, with that in mind, let's do a problem where this could occur. Let's take the function y equals x cubed minus 6x, and let's evaluate it from the interval 0 to 3. It'd be useful to see what that looks like. Kind of like this. 3 is over here somewhere. So we're going to have, I'm just going to a negative area here, and we're going to have positive area here. We don't actually have to think too hard about this. We could just use the mechanics we learned. There are 3 x cubed minus 6x dx. We just have to find the antiderivative of x cubed minus 6x. So just like you want to develop a kind of an automatic reaction to finding the derivative of x to the n, you want to do that with polynomials like this. Reverse rule tells me this is x to the 4th over 4 minus, this is 6 x squared over 2. And we want to evaluate it between 0 and 3. So, okay, 81 over 4 minus 9 times 6, 4 over 2. So this is 20.25, and this is 26. So we're going to end up negative 4.75, right? No. 5.75. So again, a negative result, perfectly valid in this context. Apparently there's more area down here than there is here. Just want to see how close we are to the break. Yeah, why don't we take a break a little early, come back, and we'll look at dealing with integrals in a more general way that will be useful. So we had some rules when dealing with derivatives that made life easier. For example, the derivative of the sum is sum of the derivative. There's a whole bunch of those rules. We're going to have to, at some point, we'll do a review before the final. But they're important. They constitute major area of knowledge that this class is about. Likewise, with integrals, there are some rules. Allow us to manipulate them and make life easier. Let's take, for example, we have some function, and maybe we have point A, point B, point C. area 1, you see, is the integral from a to b of this function. And a2 is the integral from b to c of this function. It should be pretty clear that a1 plus a2 is equal to go from a to b of x plus b to c. But likewise, you can see this is just an integral from a to c of this function. Okay. So what does this tell us? Well, it tells us that we're trying to find some integral from a to c. If it's more convenient to break it up into pieces like this, we can do that. This might come in handy if we have some function, let's say f of x equals x minus 5 over x minus 5. Well, this is a constant function, except at 5, there's a hole in it. Well, if we wanted to integrate f of x from, say, 0 to 10, we're a little skittish about what to do at 5, it's not continuous. You could just break it up into integral from 0 to 5 plus the integral from 5 to 10. Kind of dance around this removable discontinuity here. Okay. What was I writing there? I have to put my diagram back. So I have that a1 integral from a to b. 2 is my integral from b to c. And of course, a is equal to a1 plus a2. could rewrite this as moving this to the other side and moving this to the other side. I could rewrite this as integral from a to b, f of x dx is equal to the integral from b to c minus the integral from a to c not ending up where I want to be. This is what I get for not checking my work. Let me try again. We know from our formula over here that the integral from a to c is equal to the integral from a to b plus the integral from b to c. Again, we just use this formula here.
Are you just trying to show that like AB or BC is equal to CA minus the other?
Not exactly. Close. Well, I didn't really say anything about, I guess I implied here that B is less than C. But this formula works if I switch B to C. But that would mean what? That would mean this is A1 here, this area. It's equal to AC, that's A1 plus A2 plus C to D. We can subtract A1 from both sides and subtract this, and we're going to get that A2 is the integral, negative integral from C to B of x dx. Okay, this is what I wanted to show, which is if you reverse the order of the limits, you just get a negative value. So let me see if I can write that here on our list. I'm just going to write it this way. Okay, so all this is saying is that if you integrate from A to B, you get a value. If you integrate from B to A, you get the negative of that value. I don't know why that was so hard. Right. this, we can find a kind of a simpleton kind of relationship. What would f of a, what would be the integral of a to a of f of x dx be? Well, that would be the integral from a to b plus the integral from b to a of f of x dx. But this is just, you know, I can just switch these by my second rule. And make this negative, and I get 0. So here we have a nice rule. If I integrate from a to a of any function on the same point, you just going to get 0. Okay. All right, I guess I'm just going to state the next rule. I think I'm just going to state it. I'm interested in what the integral from a to b of some constant times the function is. Well, we know this is just can be evaluated by finding the antiderivative of f of x, which is just c times the antiderivative. The antiderivative of c times little f of x is just c times the antiderivative of x. So this becomes c f of b minus c f of a. Which is just c times f of b times f of a. C times the integral from a to b of f of x dx. That is to say, constants can come outside of the integral sign or be moved in as you like. So let's put that here. So those are some basic rules we have. How might these come in handy? So let's say I have some function f of x And I'm just going to draw in here. We're going to be integrating from, I guess, from 0 to, we'll call this A, make it more general. B, C, D. But we're not looking for this integral here. We're not interested in that. What we're interested in is the absolute value. In other words, we want all these areas to contribute positive area to the integral. Well, if we can find the zeros of this function, we can rewrite this as f of A to B, f of A to, sorry, I meant D here, A to B, plus B to C, plus C to D. We know that this is just, this is the negative of f of C to D. This is positive, so it's just f of x, A to B. And this is f of x from C to D. Well, f of x between b and c is negative, but if we just evaluate these integrals and subtract this, which will be negative, we will get the result we want. So I think that bears an example. So let's go back to a problem we did earlier. We wanted the integral from x cubed minus 6x from 0 to 3. And let's just change it a little. Let's say we now want the integral of the absolute value. Well, we have to find out where the zeros are. So this is x times x squared times 6. So x is equal to 0. X equals 0 makes this 0, or x equals plus or minus the square root of 6. Well, we're integrating from 0 to 3, so we're not worried about the negative square root of 6, and 0 is one of our starting points. So our function kind of looks like this. This is the square root of 6. And the way we evaluate this is we set this equal to the integral from 0 to the square root of 6, x cubed minus 6x, negative, I guess, because this is negative. And then we add it to the integral from square root of 6 to 3, x cubed minus 6x plus dx. Well, the nice part is we only have to find the antiderivative once, right? X to the 4th over 4 minus 6x squared over 2. And we evaluate it from 0 to the square root of 6 plus same thing, square root of 6 to 3. And I run out of board. Because of the calculation everyone should be able to do, but let's rewrite it. Negative x to the fourth over 4 minus 3x squared from 0 to square root of 6 plus x to the fourth over 4 minus 3x squared square root of 6 to 3. Well, 6. That's nice. 0. It's just going to be 0. So this is just going to be square root of 6 to the fourth. That's 6 squared. 36 over 4 is 9. And square root of 6 squared out of 6 minus 18. And over here we have 81 over 4 minus 27 minus, now we're going to plug in square root of 6, but we're going to get the same thing we got over here. This is negative 9. Oh, I'm going to mess up the sign if I do it that way. 9 minus 18. There we are. All right, so we have negative 9 here minus, so this is positive 9. Whatever we found before, that's 20.25 minus 27, and this is again plus 9. So we have 18 plus, this was negative 6, 6.75, and you can do the rest. Yeah, I mean, you know, again, the idea is this is how you evaluate a function if you have an absolute value sign. Now, of course, if you're lucky and there are no zeros, then it's easy. You just evaluate the integral, and it's below the line. You can just change the sign, save yourself some steps. I think I got that wrong, actually. No, I'm sorry, it is right. All right. Any questions about this so far? Again, we're now down to the mechanics again. We need to know how to evaluate definite integrals. These real-world problems actually are going to be solved this way. Yes.
So back at the second rule, when you switched around the B and the C there, yeah, it's not on the board.
You mean this rule?
Yeah, but it was the step before you got to there, so it was.
Oh, okay. All right.
And you just erased it.
Fair enough. I can go back.
So what's different or what stands out is when it goes from C to B instead of B to C. So you're going backwards on the graph.
Yeah, it's maybe I could explain that better. So from this diagram, I'm going to go about it a little differently. From this diagram, you can see that the integral from A to C is just the integral from A to B plus the integral from B to C. That's obvious. Just here, A1 plus A2 is the total area, right? Now I'm going to play a little game here. I'm just going to switch the labels. Well, now, say the integral from a to b, that's the whole area now, is equal to, wait a minute, is that what I wanted to do? Hold on. No. Integral from a to c, right? That's this area. That's equal to the area from a to b minus the area, minus the integral from c to b. Is that fair? In other words, from here to here, I'm sorry, from here to here is equal to from here to here minus c to b. Are we okay with that?
Yes. That makes sense, sure. And the point is to find out the entire area.
If we put these back, this is obvious, right? Just A1 plus A2 is our area from A to C, right? I switch these back. Now here, I'm just making a similar statement. I'm just saying the area from A to B, I'm sorry, the area from A to C, that's just this. A1 is equal to A1 plus A2, that's this integral, A to B, minus A2, this integral. You okay with that? Okay. So now I'm going to apply this rule, which says you switch these, you just get the inverse, the negative. So let me do that here. A to C of f of x dx equals the integral from A to B of x dx plus the integral from B to C of x dx. Well, that's the same formula I had over here, except that now my points have been switched. To the point being, you can switch the points however you want. The same formula applies. Is that okay? I think that was a little better. I mean, the takeaway is it doesn't matter where A, B, and C are. In fact, A could be equal to B. It would still work. Right? All right. What else have we got here? Right. These are the main rules we're going to use for dealing with breaking up an integral if we need to. There's a few more rules for integrals that we need to look at. So, So if we're finding some kind of interval here, some function. It's worth noting that we take a rectangle which represents the maximum value of f of x. On the interval, or we take a rectangle that's the minimum value, the minimum, the max. I guess I need to move this over. That this area is going to be less than or equal to that rectangle. In other words, the area under my curve is less than the rectangle surrounding it, and it's going to be greater than that rectangle embedded in it. You can think of this as a comparison rule here. So how would that come in handy? I don't have an example. I should have an example. Similarly, we have some comparison properties. If f of x is greater than or equal to 0 on interval AB, and if f of x is greater than or equal to some g of x for all x in the interval, then the interval from a to b of f of x is going to be less than or equal to, greater than or equal to integral g to x, a to b. Okay, so what is that saying? That's saying if you have some function g of x, is our f of x, and g of x is always less than f of x, then the area under g of x will be less than the area under f of x. And similarly, you can just switch the greater than to less than, and that second comparison. All right. There's just a few more things to be aware of. We can't prove these in this class, but we have some conditions for integrability. F of x is continuous on the interval that we're going to integrate over, or as at most finite number of discontinuities of I guess I should say jump or removable discontinuities. Okay, so what does that mean? You have some function, and maybe it's a step function, or maybe it has some holes in it, and it jumps around. So here's A and here's B. You can still find the area under this function. If the number of discontinuities is finite, you can see how we would use that property that I described, where you find an integral from one point to another. You just add them together and you can get the sum. You can evaluate the integral. It's a lot nicer in this way than differentiation. You can't really find the derivative over a discontinuity. Integration lets you do that. There's a nice counterexample to this. Not a counterexample, an example of if those conditions are not fulfilled. That's this function we looked at before. It says f of x equals 0 if x is irrational, 1 if x is not irrational and irrational. And we draw this kind of like this, even though this is kind of a misrepresentation. For our purposes, this function is not integral. It has an infinite number of discontinuities. All right. All right. That's the basics for definite integrals. I'm going to do a few more problems, just so you have a little more, see a few more problems. I hope I can get some assistance here. So, let's find the integral from 1 to 2 of the natural log of x. So, does someone recall the antiderivative of the log of x? Wait a minute. Is that the problem I want to do? No. I'm sorry. 1 over x. Well, I've already given you a hint. Anyone? Antiderivative of 1 over x? Yeah, that's the natural log of x. So we just end up with log of 2 minus log of 1. Anyone know how we can simplify that? the log of 1? 0, yeah. So this is just the log of 2. In some textbooks, this is the definition of the log, natural log function. Okay. Integral from 1 to 3 of x squared minus 2x plus 1. So, okay, pretty straightforward. Antiderivative x cubed over 3 minus x squared plus x 1 to 3. So what do we have here? 9 minus 9 plus 3 minus 1/3 minus 1 plus 1. So it's just 3 minus 1/3. But we might also want to know what the derivative, the integral of the absolute value is. How would I go about that? What do I need to know to do this? If you graph this, you'll see something like, imagine something like this, where it's going to cross the x-axis. Where's it going to do that? I guess we're tired out here. You get some practice doing these in the homework I'm going to assign. May have to rearrange it a little. Any other questions for today? No? Okay. All right. I will be around in my office today. You have